Hey, welcome to NASA Edge.
An inside and outside look
at all things NASA.
Oh, that's going to leave a mark.
Up next on Any Live, the mission rundown for Space Shuttle Endeavour's 25th and final mission.
We're talking with Trent Martin from Alpha Magnetic Spectrometer and Wade May with STORRM. That's 2 R's. 1 mission, 2 R's.
And AMS may just discover the origin of the universe.
Do you think they can help me find my keys? Because if not, I'll need a ride home.
For this particular mission, we're looking at the AMS.
Yep. Alpha Magnetic Spectrometer.
Also, the Express Logistics Carrier is taken up. And also, there's going to be 4 spacewalks.
Yeah, and it's interesting, Chris, and I was wondering if you could help me out. It's called OV-105. That's
yes.
Is that a code name, or what is that?
Well, OV stands for Orbital Vehicle.
Very good.
And in fact, we're going to be talking to Trent Martin from the AMS, who's a project manager for AMS, and he's going to tell us all about that magnetic spectrometer.
And that's a very complex and important scientific mission, and I have no idea what it's about, so I'm really looking forward to this segment myself.
I'm right there with you, because I have no idea. This is way over our heads here. So, what is AMS all about?
So AMS is the Alpha Magnetic Spectrometer. It's a large high-energy physics experiment that's looking for antimatter, dark matter, and to understand cosmic ray propagation in the universe.
Are we sure that that's something we want to find?
Yeah.
Antimatter and dark matter. Is that one and the same, or is that different?
No, they're different. So if you understand an atom, you have a proton, a neutron, and an electron around the outside. Positive middle, negative around the outside. Antimatter is just the opposite of that. Has a negative, large mass in the middle, and a positron around the outside. So that's what antimatter is. One of the theories of the Big Bang was that at the beginning of the universe there were equal amounts of matter and antimatter, in which case there should still be equal amounts of matter and antimatter. So the question is, where's that half of the universe that's made out of antimatter?
Could that be your half of the universe?
It is quite
it's good
possible.
to have lofty
actually.
goals. We're going to find the other half of the universe.
It's like Bizarro World.
Yeah, exactly. You know, there's a tall redheaded co-host, or what's the opposite of red hair? I don't know.
We'll have to look into that. Yeah. Now, once AMS is installed on ISS, how soon can you start collecting data?
Once we launch here in an hour or so, about an hour and a half later, we'll turn AMS on.
Oh, wow. While it's still in the payload bay?
While it's still in the payload bay. We'll leave it on up until about Wednesday night at about midnight. At 1 a.m., we take it out of the payload bay and we move it over to Space Station. As soon as we're on Space Station, which should be Thursday morning, around 7 a.m., we'll turn on AMS and we'll be collecting science.
And the AMS will actually function throughout the life of the ISS?
Right. As long as we're getting power, we're collecting data. 24 hours a day, 7 days a week.
That's a good question, though. Now, you've got it up on ISS and it's collecting data. How do you get the data? You certainly don't use the astronauts on the ISS to manage the data. Does it come down another way?
So we're collecting an obscene amount of data. 7 gigabits per second, which is way more than the space station can send down. So we skinny that down once we're on station to about 7 megabits per second. We send that down through Mission Control in Houston. Eventually it goes out to the science centers, which will be located around the world. The scientists are broken up into 2 groups, so they'll analyze the data twice, essentially, to make sure that they don't get any overlaps and to make sure that they are actually seeing what they think they're seeing. And then they'll publish from there.
Got my STORRM hat on, I've got my STORRM demo, but I want to assure the audience this is not an actual STORRM device. This is for display purposes only. That's why I get to hold it. I'd never get close to the real thing. But Wade, thanks for coming on the show. Can you tell us a little bit about what STORRM is?
So STORRM is a sensor test for Orion rail nav risk mitigation. So these are the new docking sensors that were developed for Orion, and this is the first time they've been tested in space. So we're trying to reduce the risk by making sure they work so that when Orion goes up, we make sure that their sensors are going to work the first time.
And how does it work? I mean, how do you improve docking with the ISS?
So you make it smaller, you make it use less power, and you make it more accurate.
We were actually out at Ball Aerospace back in October, and we shot a segment on it, and they talked about this VNS?
Vision Navigation Sensor.
VNS.
So it's a flash LiDAR sensor, and it is 16 times more accurate than what's currently in the shuttle right now. So the level of detail that you can get from that sensor is much, much greater.
What is the difference between STORRM system and what is being used on shuttle right now?
So on the shuttle right now, you've got a black and white docking camera, a scanning laser, and you also have radar. So we have a new docking camera in here that's 4.3 megapixels. We have a pulse laser, and that laser actually will replace the radar and the current laser in the shuttle, because this laser can go out to 5 kilometers, and right now the shuttle has to use radar in order to know where it is at that distance.
Now, I understand that STORRM in its current configuration is smaller than the docking system that's used now?
Right, so this box represents the size of the current laser system in the shuttle, and if you can flip it up, there's a see-through panel.
Oh yeah, here we go.
The actual VNS in here is about half of the volume, so we've reduced the size of it, they've reduced the mass of it, and of course the more mass and power you can save, the more oxygen you can take with you to survive.
Beyond 134, are there any other aerospace uses that STORRM could possibly be used for?
So you could use it for commercial flights. Of course, it's planned for Orion. A commercial Earth possibility would be to check deforestation, and you can also use it for hazard avoidance, like if you're landing on an asteroid or landing on Mars and you're trying to miss the rocks.
Yeah, that's very important.
Yeah, we love avoidance. People avoid me all the time. Maybe they can use that technology somehow.
On deck, a look back at 19 amazing years and 24 missions with Space Shuttle Endeavour.
Plus, an interview with astronaut Mike Good.
Did you get an interview with Mike Massimino?
No, I didn't even get to talk to the Diesch girls.
But you did try STEM bar.
If by try you mean consume several dozen, then yes.
3, 2, 1. Booster ignition and liftoff of the maiden voyage of Endeavour on a...
The Space Shuttle Endeavour, NASA's 5th orbital vehicle, launched for the first time in 1992. In its first 24 missions and over 103,000 miles of spaceflight, Endeavour has honored its namesake through challenging and unique accomplishments. Capturing and releasing the Intelsat 6 communication satellite. Completing the first Hubble telescope surfacing mission in high orbit above the Earth. Rendezvousing with the Mir space station. And many missions to help complete the construction and further work of the International Space Station. Now Endeavour is fueled and ready to fly its 25th and final mission. And all the hard work and dedication of thousands of technicians, mechanics, scientists, engineers, and astronauts will reach its zenith as we get a final go for liftoff until OV-105 touches the ground one last time. Thanks, Endeavour, for a job well done.
You've been up on Atlantis for Hubble, and in Atlantis again up to the station. What's the difference between when you went to Hubble? Was it seem like it was isolation because you're only with your team as opposed to going to station and you had other crews and you had this big, huge structure in front of you?
Oh, absolutely. They were two totally different missions. I went to Hubble first, and so I thought, floating around on the mid-deck of the shuttle was really cool. I mean, floating in space is a lot more fun than I expected. But then to get to station and to see how big it is, and there you can actually fly around because there's so much room in the modules that you're like Superman, you push off and you can go flying for a long ways, before you'll hit anything, if you're good.
Right.
It takes a while to...
I was going to ask you, did it take you a while to get good at space flying?
You have to learn how to control your body, and the first time you're just banging into the walls, and somebody has to go behind you and put everything back, and you're not everything's on Velcro, so it's just a train wreck.
Now, did you find that your EVAs with Hubble were a little bit more difficult than station, or vice versa, or were they pretty much the same?
They were very different. I would say equal difficulty, but just totally different. Again, the spacewalking experience from the shuttle and Hubble going out the shuttle's airlock and into the payload bay. A lot of the Hubble work was more like surgery. You know, we were inside the Hubble Space Telescope using power tools, but having to be very careful because we were there to fix the telescope.
Right.
And they kept telling us very clear in training, do not break the telescope. So we
And
were
yet
very
Massimino
careful.
was on the.
Hey, we're not going to hold it against him for.
So what do? We
pulling a
stick
handle.
the biggest guy we got inside the telescope, Mike Massimino. He was very careful though. He was a statue in there, and he was like basically working with one hand, didn't breathe for 8 hours. Very incredibly incredible
gift.
job. Yeah.
Well, you know that I guess we can say this on air now is that your mission,
I guess we can.
Your first shuttle mission might not have happened if it wasn't for the experience at Daytona that we had. you
That's
know?
right. I think it's a prerequisite.
That's
you
right.
know.
If it wasn't for the officer to almost
He cut me a
take
break
you away.
there.
Yeah, he
That's
sure
right.
did. Didn't he?
It could have gone either way. That was like the turning point in my career right there.
No, that was a
Thanks
great.
to you guys.
That was a great.
Trying to
We
get me
actually saved. You actually owe us. We saved you from a.
Oh
from,
yeah,
from
I owe you guys.
Why don't you tell the story real quick?
Yeah, real quickly. We were out at Daytona, and it's a
50th
point
anniversary.
before the race where you can go out on the track.
Honest mistake. That's all I got to say.
Yes.
2 words for you. Honest mistake.
So a lot of people are autographing the wall, and we're up there, and Mike says, "Hey, you want me to go autograph the wall?" And we thought that'd be great. So we handed him a marker. He goes up. He's writing away on the wall, and all of a sudden, 2 police officers show up, and they actually inform Mike that it's not okay to write on the wall.
I thought it was part of the routine.
Right,
I thought it was part of the show. I'm
He
like, are
thought
you
we were
serious?
busting him, so he told the cops that they were crazy.
No.
And no. And anyway,
I was very apologetic.
You were very
yes.
apologetic.
And
Yes.
when they found out he was an astronaut, they actually asked to have some pictures.
Then we
taken.
started taking pictures. And,
Yeah, and having fun.
Yeah.
But it was a great moment and very scary for me, as I thought I might be responsible for sending an astronaut to prison.
I'm here with Michaela and Shannon Diesch from Michigan, and these 2 sisters were the winners of the Conrad Foundation Spirit of Innovation Award in 2010, and they won for their space nutrition bar. So what ingredients go into your bar?
So the name of it is the STEM bar is what we're calling it right now, but we're working on the name still. And it's a cinnamon cranberry apple flavor, and there's cranberries and apples obviously and cinnamon. And then it's mainly oat based with nuts in there as well. And it's really, really good.
How much of this did you eat before you actually came up with the final product?
I had so much. Some of them were not the best tasting things ever, but others of them I liked, but then they didn't fit the requirements. So we had to find the perfect mixture of good tasting and fitting the requirements.
So I understand you all, finally got your final product and manufactured it in a food lab near where you live. But did you start first in your home?
Yeah, we did. It was in our kitchen trying to mix pots together and heat stuff up and then pour it together. And we didn't have everything we needed, so it was a lot of improv, like trying to make it work.
What went through your mind when you found out that you actually won?
I was so surprised. Like when they announced our name, I was like, no, they didn't mean us. They meant someone else. I went up there and pulled Shannon up, and we're like, oh my God, we won. It was amazing.
Did you cry?
Shannon almost cried.
Almost?
Almost.
She looked like it.
So the next step, you get involved with NASA. Tell me how that happened.
Well, after we won the competition, we figured it's a bar designed for NASA. It should go up into space. We got a call from someone at the Conrad Foundation because we've been working closely with them. They said that they think they found someone who'd be able to help us get our bar to the space station. So then we had to go through all their testing and make sure everything was perfect. It passed the microbiological testing and everything. So it was a really awesome thing.
So your bar that you have here is now on STS-134. How does that feel?
It feels incredible. Like every time I look over there, I'm like, my bar's over there, and I can't wait for it to go up. Like if I can be here to see it, it'll be incredible. Like just thinking something I made is on there and it's going up there. It's just incredible.
Do you know how many bars are on the Endeavour?
I think between 6 and 10.
Between 6 and 10?
Yep.
How does this taste?
Amazing. It's the best bar I've ever tasted.
It's the best bar you've ever tasted?
Best bar I've ever tasted.
I know Blair wishes he were here to try this instead of me, but we'll give it a try. This is pretty good. Space nutrition bar made by the Diesch Sisters out of Michigan. This is great. I need some fluid right now.
Before the launch, Tom Horvath and Ann Micklos talk about HYTHIRM and the data they're collecting during the mission.
the protuberance.
Exactly. Plus, the weather looks good for another successful launch.
All systems, go.
The guys that are designing the next generation vehicles, we've got to be smarter. We've got to have these thermal protection systems that obviously protect the astronauts during reentry. But to really be economically viable, we've got to make the thermal protection system a lot lighter and less expensive to put on the vehicle and maintain. So what we're trying to do is really get some high quality flight data that we can go back then and validate our engineering tools and models so that the guys that are actually developing the thermal protection systems can really understand just how thick that tiles has to be.
Now we have an example of an actual tile that's used on one of the shuttles.
That's right.
Or actually, you would have something like that very similar on Endeavour.
Actually, what's on Endeavour is the exact same tile.
Okay.
It has this nice little, what we call protuberance on it.
Yes.
But it also has a little thermocouple that sits downstream of it as well, that this particular tile doesn't have. But from a tile standpoint, they're identical. Believe it or not, this is the lowest point on the orbiter.
Really?
It is. This little half inch. You think, oh my gosh. But normally, there's about 22,000 tiles on the bottom of the orbiter.
Okay.
And each tile, the steps in between the tile is about the thickness of a credit card. So now we're putting something underneath the orbiter that's a half inch.
Wow.
It's kind of big.
Yeah, that's
big.
right.
It's
That's right.
real big.
And they let you do it too.
I know
Yes.
it. They did. And this is actually our 5th flight of flying with a protuberance on the tile. And with anything you do, you start with a smaller height. We started with 1/4 of an inch. They had predicted we'd see, 2,700 degrees, and actually we ended up only seeing 2,200 degrees. And the reason we could see that, we actually have a little temperature measuring device, a thermocouple that's embedded into the tile that will measure those readings.
Okay.
What we've learned is that the models that have been created are much more conservative than what we're actually seeing on orbit. So even after that first flight, we were able to learn and then update the models to what we have today.
And you could make this tile just a little bit thinner. You know, it saves a lot of weight.
Right,
So
absolutely.
That's critical.
And what you have in your hand, you actually have a model of a shuttle that actually has wind tunnel data.
Yeah, I have a replica here of a shuttle model. This is about the size we actually test in the wind tunnel.
Okay.
On the lower surface here, Chris, I have a heating pattern. And this heating pattern on this surface is representative of what we measured actually in the wind tunnel. So like the areas where you see the reds, the yellows, those are areas where you'd have higher temperatures, and the areas where blue, much lower temperatures. About right here in the wind tunnel, we actually had modeled a little bump to the model scale, and that's right where it is actually on Endeavour. And you can actually see the heating footprint downstream of that. So what we do then is relate these measurements that we make in the wind tunnel, these global measurements on the vehicle, then to what we correlate that against what we actually see in flight and versus what we actually see with our modeling.
Now, shuttle's going to retire. This is the second to last flight. We have another one in next month. Where do you see this type of thermal imaging in the future once the shuttle retires?
Well, we've actually kind of started moving in that direction, Chris. Last December, we were supporting the Commercial Crew and Cargo Office at Johnson, and they were doing a demonstration flight. One of the commercial guys was launching their rocket from Kennedy. We actually measured the temperature increases on its heat shield. It looked like much more like an Apollo capsule than the shuttle. But so we're kind of moving in that direction now, where we're going to be supporting potentially the commercial sector.
Well, speaking about thermal imaging, at what altitude are you actually getting thermal image of Endeavour when it returns?
At the speeds that we're kind of targeting, this trip was designed to cause this turbulence on the lower surface around Mach 18, Mach 19. I think the orbiter's around 210, 220,000 feet.
Oh, wow.
It's a good question, because the aircraft is actually much lower, around 25,000 feet. So the distance between the shuttle that's coming in and the aircraft that's taking the pictures, you're anywhere from 25 nautical miles to 40 nautical miles. And it's kind of intriguing. The guy that takes the pictures, I've asked him, what does it feel like when you're up there? He's kind of described it to me as if you take a soda straw, Chris.
Okay.
And you know, if we look back at the VAB building, I see some of the birds flying out there, and try to pick up one of those birds and follow it through that soda straw.
It's very hard.
It's very challenging. So they have very sophisticated equipment. You know, we work with the guys at Johnson to understanding just exactly where the shuttle's supposed to be, at what altitude, and they are very sophisticated equipment in terms of being able to point very accurately and pick up that shuttle as it just appears as a bright star initially, and then as it approaches the shuttle, takes about 2 minutes for it to actually come over the aircraft.
Right.
I only get these global measurements for a very short period of time, 20, 30 seconds, whereas her thermocouples are on all the way from, orbit all the way down to wheel stop on the runway. So they really do complement each other, the data that we get.
Well, thank you so much for being on. Let us know what the data looks like after the Endeavour lands and see if you get great data.
Absolutely.
Thank you so much.
Absolutely.
This is your first launch. I mean, are you pumped?
I'm pumped. I've been around NASA for almost 16 years, and it's so funny coming toward the back end of the shuttle program will be my first shuttle launch. That's like almost unbelievable.
I mean, unfortunately, that we were here a couple weeks ago, and we had to scrub the mission.
Our first scrub.
My second.
Your second?
Yeah.
But you can feel the energy around here. Lots more people are coming out and approaching the clock. It's, the excitement is building, lots of activity, very exciting, and obviously a very important moment for NASA and Endeavour.
Hey, check out some quick facts for the Shuttle Endeavour. Through STS-130, which was the last mission for Endeavour, it's flown over 116,300,000 miles.
Now,
in space.
Does that exceed the warranty?
Is the shuttle good for every 100 million miles? I don't know. It's been in space 283 days. It's orbited the Earth 4,423 times. And we've had a total number of 166 crew members, not including, of course, 134 that's going to be launched here momentarily in less than almost 3 minutes.
8, 7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Roger, roll, Endeavour.
Houston is now in control. Endeavour.
Go, Endeavour.
Awesome.
The roll program underway as Endeavour begins the heads down position on course for a 51.6 degree, 136 by 36 statute miles.
Congratulations to NASA and the entire STS-134 team for a successful final launch for Endeavour. And don't forget to join us for the final space shuttle launch with Atlantis coming soon.
And be sure to visit our Facebook fan page for additional interviews and coverage of STS-134.